In this video, I want to look at some of the ideas involved in the reason why some of the things that we're going to talk about are true. To start with, I want to think about what we'll call the after a while effect. Imagine that you have two sequences, the A sequence and the B sequence. Suppose also that there's an integer capital N, so that when the index is bigger than that capital N, Bn and An are the same thing. They are the same numbers after a while. If the limit as n tends to infinity of an exists, then so does the limit as n tends to infinity of bn, and furthermore, they're the same number. If the limits don't exist, the way in which they don't exist is the same, because after a while, looking at b numbers is the same as looking at a numbers. Suppose that you have a sequence of numbers, a1, a2, and so on, and you begin to build the partial sums for the infinite series. S1 will just be a1, S2 will be a1 plus a2, and so on and so forth. In a similar way, imagine that you have numbers b1, b2, b3, b4, and so on, and we build partial sums based on those numbers. To avoid confusion, I'll call these the R numbers. What I want to think about is what happens if after a while the b numbers and the a numbers are the same. Let's think of partial sums for these two series, Sk and Rk. Be sure to pick the k so that it's bigger than n. S number k is a1 plus a2 out to a number capital N plus an plus 1 out to ak, and likewise for the Rk. Once the index on an A number or a B number is bigger than capital N, though, the B numbers are the same as the A numbers. Because both of these are just ordinary algebra sums, I don't feel bad about grouping the first capital N terms together in both of them. Also, for the b numbers, once b is past capital N in index, the b numbers are the same as the a numbers, so I don't feel bad about that either. Now, k does not depend on n, except that k has to be bigger than n. K could be billions of times bigger than n. If I call the sum of the first n terms of the A series alpha, and I call the sum of the first n terms of the B series beta, then what we figured out is partial sum Sk is this constant plus this sum. Rk is beta plus that same sum. If you calculate Sk minus Rk, you find out that the value is alpha minus beta for all index k bigger than capital N. This says that the partial sums for the two different series differ only by a constant when k is sufficiently big. I'll rewrite this way. I'll think of what happens when I allow the k to become indefinitely big, which in particular means that it's bigger than capital N. This term is a constant. It doesn't have k or n or anything in it. If these numbers approach some limiting value, then the sk's will approach that value plus this constant. If the rk's converge, then the sk's converge as well. If the rk's diverge, since sk differs from these divergent numbers only by a constant amount, then the sk's would have to diverge as well. You can rearrange this and make exactly the same argument if the sk's converge or diverge. If the sk's converge, the rk's converge to the value of the infinite series for the a numbers plus alpha minus beta, so that will converge as well. If the sk's misbehave as I allow k to become indefinitely big, the rk's, being the difference of a constant with something that's acting badly, will itself act badly. I think this is much more understandable than doing an epsilon delta argument. What this means for me in practical terms is this. If I want to know whether an infinite series converges or diverges, I could leave out the first 50 terms and it wouldn't matter. I could leave out any finite number of terms. I could alter a finite number of terms to have different values than they had originally as well, and none of that's going to make any difference. If one of the series converges, the other one does as well, and vice versa. Another fact that I'm going to need to know here is this. Suppose I have a sequence of numbers which are all positive, P1, P2, P3, and so on. Also, suppose that the infinite series based on the p numbers diverges, that is to say it doesn't exist. Then the way that it doesn't exist is that way. Remember that that's a shorthand for the limit of the partial sums fails to exist in the manner where they all become indefinitely big as you allow the index to become big. I'm going to need this fact shortly, so we'll go ahead and convince ourselves of why this is. Imagine constructing partial sums for such a series: P1, P1 plus P2, P1 plus P2 plus P3, and so on. All of the p numbers are positive, so P1 plus P2 is larger than P1. P1 plus P2 plus P3 is larger than P1 plus P2, and so on and so forth. This tells me that the sequence of partial sums is an increasing sequence of numbers. A sequence of numbers is either bounded or it isn't. In this situation, what would happen if the sequence of partial sums for the p numbers was a bounded sequence? Suppose that these partial sums form a bounded sequence. We've just convinced ourselves that the sequence of partial sums of p numbers is increasing. If this were the case, these partial sums would form a bounded, monotone increasing sequence under the circumstances that we're talking about, positive p numbers and this infinite series diverging. We've already seen that the partial sums of the p series are increasing. A sequence of numbers is either bounded or it's not bounded. What would happen if the partial sums formed a bounded set? These partial sums are getting bigger, so they're monotonic, and if they're bounded, there's an upper bound. A monotonic bounded sequence of numbers converges. This would tell me that the sequence of partial sums converges. This would tell me that this infinite series converges. But the premise that we started with was that the series diverges. If I say that I've got a series that diverges of this type, and then I try to claim that it's bounded, I get myself a contradiction. So it must be true that if I'm looking at an infinite series of positive terms and it doesn't converge, it's impossible for it to be bounded. It must be unbounded. In these partial sums, if I include enough terms, I can make the partial sum as large as I want to make it, which is this statement. When I figure out the next partial sum, I'm going to add p number k plus 1 in, which will move me further to the right. As I add more of the p numbers in, this will move me further and further to the right, and there'll be no way for the partial sums to approach L. We're now in a position to talk about what people call the direct comparison test. Imagine that I have two sequences of numbers, the AIs and the BIs. All of the AIs are at least 0, and all of the BIs are at least as big as the AIs are for every single index I, or after a while. Then I can make two statements that are reliably true. Firstly, if the infinite series based on the outside numbers converges, then the infinite series based on the AI numbers converges as well. For right now, I'll just assume that this inequality is true for all I. You can make a modified argument if it's only true after a while. If the sum of the BNs converge, then each one of those sums is less than the limit of that series, less than capital B, for instance. Because of those two facts, I can say that 0 is less than or equal to A1, which is less than or equal to B1, which is less than the value of the B series. Also, 0 less than or equal to A1 plus A2. A1 is less than B1. A2 is less than B2. B1 plus B2, though, is less than the value of the infinite series of the B numbers. You can repeat this argument. This shows that the partial sums of the A series are bounded, but also, because none of the A numbers are negative, this says that this is monotonic. Monotonic non-decreasing, if you want to be picky about it. That tells me that the sequence of partial sums of the A numbers is a bounded monotonic sequence, and we know such things converge. Now, on the other hand, if I have the same situation and the sum of the A numbers diverges, then that sum must diverge to plus infinity because of the comments that we made before. On the other hand, I've got this inequality. A1 is less than or equal to B1, A2 is less than or equal to B2, and so on and so forth. Partial sum number k for the A series is less than or equal to partial sum number k for the B series. Or saying it backwards, the partial sum of the B series is at least as big as the partial sum of the A series. But because of what we know about such series, the A partial sums become indefinitely big, and the B partial sums are in fact bigger than or equal to something that's becoming indefinitely big as we add more terms on. That means that the sum of the B numbers must diverge to infinity, if we want to think of it that way. Next, I'd like to present a rationale for why the integral test works as it does. So we're going to have the same premise as the integral test. I've got an infinite series that I want to think about convergence or divergence. Each individual term is positive. Each individual term is the value of some function f evaluated at the index of that term. Function f is continuous, positive, and decreasing on the interval from 1 to infinity. We'll get this idea right by thinking about the area under that curve. The area under the curve of y equal f of x starting at x equal 1, and for us right now it'll be enough to go to x equals 5. Obviously, I could calculate that integral just as is if I could get an antiderivative, but I want to think about it another way too. I can think about the integral from 1 to 2 of f of x, the integral from 2 to 3 of f of x, from 3 to 4, and from 4 to 5 separately, and then add up all of those contributions, and I would get the integral from 1 to 5 of f of x dx. But another thing that I could do is, for each one of these integrals, I could approximate the integral either with a rectangle that's too big or a rectangle that's too small and get estimates for these things. Draw the rectangle that starts at this point, has constant y coordinate until you get to x equal 2. The width of that rectangle is the horizontal distance from 2 to 1, which is 1. The vertical height of it is f evaluated at 1, which would be a1. The area under the curve is contained within this first red rectangle, so that tells me that the integral from 1 to 2 f of x dx is less than or equal to a1 times 1, which I'll just write as a1. When I'm looking at the chunk from 2 to 3, this horizontal distance is 1 again, and this vertical distance is f of 2, which is a number 2. So this second integral, this second amount of area under the curve, is certainly no bigger than a2 times 1, which is a2, and likewise for the other two pieces. Now, on the other hand, if I look at x equals 2, the y-coordinate on the graph is f of 2, which is a2. The horizontal length across the bottom of the first green rectangle is going to be a2 multiplied by 1, which is a2. And then, reasoning in the same way as before, we can write down the following results. I think the pattern to the indexes and the limits of integration should be fairly clear. Lower limit of integration 1, index 1. Lower limit 2, index 2. 3, 3, 4, 4. On the other end of the spectrum, upper limit of integration 2, index 2. 3, 3, 4, 4, 5, 5. I believe that it's fairly clear that this pattern will persist even if you were to include more of these little pairs of rectangles. If we add up all of these inequalities, we'll find something out. This sum is the same as partial sum number k of the infinite series based on the a numbers, except it's missing a number 1. When I add up the area from x equal 1 to x equal 2, then from 2 to 3, then from 3 to 4, all the way down to k minus 1 to k, I'll get the area starting at x equal 1 and ending at x equal k. I'll get the integral from 1 to k f of x dx. And if I add these numbers up, I actually get one of the partial sums. Let me rearrange this a little bit. So what I know is partial sum number k minus a constant is less than or equal to the integral from 1 to k f of x dx, which is less than or equal to partial sum number k. Notice that I had to use all of my assumptions here. I had to assume that the a numbers were positive and decreasing, that a number I was some function f evaluated at x equal I. The reason that I wanted it to be continuous is so that I'm for sure that the integrals that I'm looking at, these integrals, will all make sense. This is going to let us state something. I want to look at 4 different cases. Number 1, what if the sum I equal 1 to infinity of ai converges? That means it converges to some actual number that I might as well call capital A. As I allow the index to become indefinitely big, those numbers increase and approach A. That means that the corresponding integral is less than or equal to a constant. Therefore, the integral sequence, integral from 1 to 2, integral from 1 to 3, integral from 1 to 4, and so on, is bounded above. On the other hand, every time I increase the interval of integration, the integral gets bigger because I'm integrating a positive function. So the sequence of integrals, integral 1 to k f of x dx, is going to form a bounded increasing sequence of numbers, and a bounding increasing sequence converges. On the other hand, suppose it were known that the infinite series diverges. That means that the partial sums, sk, become indefinitely big as I allow the index to become bigger. That means that sk minus a constant also becomes indefinitely big, and the integral from 1 to k f of x dx is going to be larger than numbers that, when I allow the index to become big, becomes indefinitely big. If the sum of the infinite series diverges, this half of my inequality forces these integrals to diverge as well. What if the improper integral from 1 to infinity f of x dx converges? Each partial sum, sk, and then subtract a1, is less than one of those integrals, and each one of those integrals is less than the thing that the sequence of integrals converges to. We'll say that the integral sequence converges to capital A because capital A is a area. Sk is no bigger than capital A plus A1. Sk is bounded above by a constant, so the sequence of partial sums, Sk, is bounded above. On the other hand, since the numbers I'm adding up are all positive, the SKs form an increasing sequence of numbers. The SKs form a bounded, increasing sequence of numbers. Therefore, that sequence of numbers converges. Lastly, what if the integral from 1 to infinity f of x dx diverges? We've already seen that if that kind of thing happens, then the integrals themselves, integral 1 to k f of x dx, have to become indefinitely big, because if that didn't happen, you would have a bounded increasing sequence which would converge. So as I allow the k to become large, these integrals can be made as large as you would care to make them. On the other hand, one of the partial sums will be larger than these numbers, which you can make as large as you care to make. That means that the infinite series has to diverge to infinity as well. So what have we figured out here? Under the hypotheses of the integral test, there's only 4 different situations that you can have something converging or diverging, and the other thing converging or diverging. What we've convinced ourselves of is this. If the series converges, then the integral converges. If the series diverges, then the integral diverges. If the integral converges, then the series converges. And if the integral diverges, the series diverges. The behavior of convergence or divergence, assuming that the hypotheses of the integral test are valid, what we find out here at the very end is as far as converge or diverge, the two things act the same. The infinite series and the integral either both will converge, that would be cases 1 and 3, or both of them diverge, that will be cases 2 and 4. This is the reason that we believe this integral test is okay to do. This video is getting a little bit longer than I wanted it to be, so I'm going to stop there. There will be a Why Is This the Way It Is video number 3 coming real soon. Until then, I hope everybody's having a good day. I'll talk to you again soon.